Well, welcome back to our course on system engineering. We're rapidly getting through this last supplemental topic area. And so we talked about graphical modeling techniques, which starts to get into some of the graph theory ideas we spoke about. We have talked about decision analysis for design trades, and we gave some examples of that. And now in this chapter, we're going to be talking about the science and analysis of systems. And so in some ways, this is going to be a fairly abstract and maybe complicated lecture, but I'm going to try and streamline it. So hopefully you'll get a chance to grasp the concepts and have it presented in a couple different ways. So maybe you'll get the understanding and have some good takeaways as you go out and start to press forward in your system engineering career. So this chapter addresses the bedrock of the science of system and general system theory. And so we'll get a chance to begin to see how that actually works. General system theory, system science, natural systems, cybernetics, and system thinking. Engineering successful systems accounts for the pervasiveness of the uncertainty throughout the system life cycle. And so that's where we're trying to help out by embracing and bolstering system engineering and model-based system engineering. Successful engineering is critically dependent on system analytics, quantitative characterizations of the system, system dynamics, constraints theory, and approximate methods. And so we'll show how that works as we go through the material here in this chapter. So in the textbook and what we have here for this lecture, here is an outline of what we'll talk about. General systems theory, system science, natural systems, cybernetics, system thinking, quantitative characterizations of systems, system dynamics, constraint theory, and guesstimation. And so since this chapter contains very complex information, we'll provide a summary overview first and then survey the details. So this is taking the information in the textbook in the summary section, and we're going to go ahead and start with that. And maybe this will give a context, and that we'll just go at a higher level for a bunch of charts in this chapter and only to drill down into a few of those things. So system theory is applicable to human design that is engineered, biological, and social systems. And this is starting to have an emergence in these areas, say like system biology. The realization, operation, and support of systems necessitates a system approach, integrating various disciplines with scientific generalists performing the system function, integrating the parts into the whole greater than the sum. And that's an important reminder, the whole is greater than the sum. System science is a science of complex systems, that the science of the wholes, emphasizing how systems behave as a whole without explaining system parts. So you have a lot of things that are, you could say, are black boxes, and you're hooking them together and then you're explaining that. System behavior can be explained without reductionisms, with high-level characterizations to estimate behavior and establish feasibility early on in engineering of systems and reducing risk. Natural systems constitute living and non-living systems found in nature. Structures found in nature can be reverse engineered and applied to the engineering designs of system. And there's a lot of interesting work being done in that area. Cybernetics integrates the applied mathematics of control theory and information theory to achieve the desired regulation for complex systems with complex uncertainties. So having a proper control and a flow of information is vital for a system. Information theory characterizes the variety of allowed inputs to the system, as well as the disturbances and noises using the measure of entropy. System thinking provides a holistic look at the whole of the systems, interrelationships with outside forces, and the properties of systems, especially emergence and stability. Quantization characterization of a system is done examining complex systems operating in a context of uncertainty. The treatment can be simplified to emphasize key concepts using approximate models to assess the feasibility and meet performance requirements. System dynamics is a stock flow feedback structure modeling of the system in operation. The key is the Answers and solutions to the observed phenomena may be non-intuitive without analysis, so analysis can be critical. Constraint theory determines a well-posedness of the set of often disparate, interrelated, multidimensional models, often from different organizations within the enterprise to describe the systems. So there's going to be a variety of constraints, and the system engineering team needs to make sense of all that. Models are based on physics, objectives, behavior, preferences, and costs. Constraint theory determines the internal consistency of a system's integrated mathematical model and whether requests for information out of the model are allowable. Guesstimation is an approach to make good approximate estimates with little or no data. So imagine that with little or no data, you can come up with some kind of an estimation. An unknown dependent variable is determined within an order of magnitude by structuring the solution as a product of its independent variables and making assumptions about their values. And finally, making good approximate estimates with little to no data and little time is a critical engineering skill and is of value as a sanity check of more detailed models and data. So just to reflect back, this is that outline here that we're covering in these topics. We went ahead, had a summary of these things first, and now we're going to start to get into the details. And some charts will go into more specifics, and others will just keep it at a high level. So for general system theory, this is where we get this idea the whole is more than the sum of the parts. Its foundation as a basic science applicable to human design engineered, biological, and social systems. And it provides a successful realization, operation, and supportive systems, necessitates the system approach integrating multiple heterogeneous disciplines. It needs scientific generalists to perform the system functions. And the general concepts are feedback, control, stability, and probability. So feedback, control, and stability, they drive the system to a desired goal and keep it there. Probability accommodates a real-life phenomena of uncertainty. And the starting point is create a mathematical model of the system. And so that's something that's going to be needed if we're going to be doing the analysis to have a mathematical model that we can manipulate. So we have a couple charts here that start to develop the mathematics. I'm not going to go over this in a lot of detail, but you can have sets of simultaneous, perhaps nonlinear, perhaps partial differential equations. So you're going to have a bunch of equations, and the applications can be found in engineering, biological, and social systems. And so there's references in the textbook you can look up if you like. You can have models of growth and decay. How do things change with time? So you want to be catching the the time, the temporal perspectives of that. You can have an expansion, say like a Taylor expansion. And so you can have as much fidelity as you want, or you could chop it off after so many different parameters here, maybe to 3 as shown here, or you can go further. And then we can make a number of different types of approximations if we're just trying to get the major trends for growth or decay. You can also be using logistic curves for doing this. And so you can look that up in the textbook to get some more insight about that. You can have competition in terms of possible solutions, and you can play one against another. And so that's something that can be done. So system science, it correlates general science theory with applied science under the general name of the system science. It characterized systems science as the science of complex systems and the science of the wholes. And there's more details here, but of special interest are emergent behaviors that are non-predicted based on the integration of the behaviors of the individual parts of the system. When you stick things together and you have a closed system, feedback, control, and stuff like that, there are things that start to interact with one another. And that's what we're trying to describe here when we use the term emergent in this context. So leveraging system science in the engineering design of systems, not having to perform reductionisms to explain system behavior is an advantage. And so this is what we want to be leveraging. So in the engineering design of systems, early in their concept of formulation and roughing out before committing to development. So that's what we're using system science here. A high-level characterization is used to estimate behavior and to establish the feasibility early on, thereby reducing technical risk. For natural systems, these can consist of living and non-living systems that are found in nature. So say in biology, the competition in an exponential growth or decay of two players can be described by equations. And so this just another area where we can start to be looking at, say, competition for which provides a better way of viewing the details we're trying to cover. Biomimicry in the engineering design of systems. Structures found in nature are reversed engineered and applied to engineering designs of system. You can think of like the Japan's bullet train. They try to formulate the nose of the bullet that mimics the beat of a bird to a kingfish bird to mitigate severe vibration and pressure changes on the passengers when the train enters a tunnel, and mitigate loud tunnel booms as the train exits the tunnel. Okay, for cybernetics, this is used to explain the regulation and self-regulation using compensators and closed-loop feedback servo mechanics to control and stabilize biological, social, and engineered systems. Cybernetic integrates the applied mathematics of control theory and information theory to achieve the desired regulation, even for complex systems with complex uncertainty. Then we have information theory as well, that characterize a variety of allowed inputs to the system, as well as the disturbances and noises using the measures of entry in bits. So cybernetic systems have time-varying inputs and outputs related to a transfer function characterized by the integral differential equations. So you have a black box of a function, you have an input and an output, and they all have a temporal value. So there's more details here. The solutions in the frequency domain can then be translated back into the time domain using the inverse Laplace transform. So we can be using transforms back and forth, say using the Laplace transform to help us to better characterize things. This is just more details on the Laplace transform. This is in the textbook. I'm not going to go over this, but basically you can go from either a temporal domain or back and forth to another domain. And so whether it be in the spectral domain or something like that. And so we're showing how that would work here with Laplace transform. There can be closed loop system stability and regulation. And so this is some of the details we're not going to go into as much as due to time, but we have closed loop theory. So we're getting into controls, and we're also talking about stability and the regulation, how to make things perform well, how to make sure that things stay stable, and have a control, a closed loop control, so we can have that go on and maintain an operating point that we would like to be at. So here's a generic feedback control system block diagram. And so you have a compensator, the system under control, and you have this feedback that it's looped back in. And so this is the basic concept for a first order control system. Disturbances and noise, this is something that can happen if you're thinking of a communication system or a control system, but you're focusing on different frequency domains. And so that's something that also is going to have to be put into part of the analysis as you're trying to characterize a system with your models and try and have it as closely replicate what would actually be a real system. You can have compensation for disturbances. And so things that you can do that you know these disturbances are there, so you can compensate. You can have a number of different ways of doing that. And so when we get into the transfer functions for these things, they can get a little bit complicated. And here we're seeing some examples of some of these functions that are being played out. And so, but I'm not going to go into that much detail, but there's a lot of deep, rich body of knowledge that's in this area of engineering control systems. So here is a flight control system block diagram. You can see that this is getting a lot more complicated. You have the engine, the actuator, and the aircraft, and you have putting this disturbances into the channel. And so we're seeing that. And then there's a closed loop return that also gives some feedback. And so these are the equations for the model that's used for each one of these elements. Here's another example of compensation for disturbances for aircraft flight control example, just some more details. I'm not going to go through this. And then compensation for disturbances in the time domain. So you can have a couple different ways in which you can be doing compensation. So that's kind of a quick tour of what we were talking about, cybernetics and control. Now we're moving on to system thinking. So we kind of make some abrupt changes to various topics. And so that's one of the reasons why I wanted to start out with a summary and an outline. So system thinking provides a holistic look at the whole of systems, interrelationships with the outside forces, and the properties of systems, and especially emergence and stability. So causal loop diagrams can be the basis for quantitative modeling to assess spatial and temporal performance. And so there's a variety of things that start to be coming in here as we're listing here. So in terms of system thinking, archetype of tragedy of the commons. So this is just something that is also developed in the textbook for another area in this system thinking ideology. So systems taxonomy, distinguishing hard system thinking as a engineering contribution contrasted with human-centered soft system thinking. So we can do this comparison. Humans have the ability to think well in soft system thinking. Systems are more designed to be doing hard system thinking. So it's basically things are programmed to do this or that, and it needs to know when that occurs. And so we need to play back and forth between those. So we can be thinking of something called Systemogram as a conceptual model to show the relationships, influences, and systems, and the systems of systems. And there are some ways of thinking about that in SysML, but it also talks about Petri nets as well as another way to capture that. Here's an example of a systemogram of the elevator control system. And we can see the various things that are taking place. You have the entities of the elevator and the passengers. And then there's various ways how things engage through that with the other actors and activities that are going on as well. For quantitative characterization of the elevator system, here's just some more details, and we've talked about the elevator system in a couple different ways. I'm just going to show this for a minute, but I'm not going to really go into this since I think we covered the elevator example pretty well. Here is an example of a threshold and objective performance requirements for the operational phase of an elevator during peak demands. And so now we see these performance requirements and quality type of requirements that are laid out, where we have a threshold that these are the must maintain. An objective is we would like to have something a little bit better than that. And so we're seeing two categories of requirements spelled out here. For performance requirements, there are interdependent. One thing can be related to another in some form or another. So say like the average wait time and the transit times are dependent. Velocity then is derived from performance requirements, constraints on acceleration and change in acceleration bound the maximum number of building floors. And the average wait and transit times are critically dependent on the number of elevator cars in service and stochastic demands for service. So just another thing to keep in mind. Just some more discussion on stochastic properties of elevator services. You can look this over, but I'm just going to go ahead and skip over this. Then for elevator analytics, even more, we have the external inputs, internal outputs, and engineered values for the operational phase of the elevator. And here's just some more details of that design. The elevator engineering design problem. And so first thing, before you can solve a problem, you have to define what the problem is. And so this is one of those things that would come into that. And as we're doing this, the system thinking, where we want to be capturing these types of points. The elevator engineering design choices. And so you have a couple different approaches. Accelerate the elevator from one stop to constant velocity, or accelerate the velocity to a midpoint between stops and then decelerate to begin at the midpoint. And so maybe you've been in one or both of those types of designs. We have some more details. We have the equations for the constant velocity approach, and some exceptions to the constant velocity approach. So we're still developing the elevator analytics. We have the information and the physics and the math to derive the maximum velocity that's shown in this chart. Then we have derived values, derived requirements for maximum velocity of the elevator in meters per second, both the threshold and the objective. We can also determine the average transit time. So this is going to be dependent on a variety of factors. And so here we just start to develop that, and I'm not going to go through this in detail. We have here the maximum number of building floors to meet performance constraints for threshold average transit time of 90 seconds. Maximum number of building floors to meet the performance constraints for a threshold average transit time of 60 seconds. So some more supporting details. We have the ability to determine the average waiting time. So that's spelled out here. And then we have a discussion here on elevator traffic analysis and sizing. And so this is focusing on an elevator, but having a traffic model to help determine the sizing is a useful endeavor in just about whatever domain that you're thinking about. Since I have focused periodically on satellites and CubeSats, if you needed to get complete coverage, just like having enough elevator coverage, you're going to be needing to do some analysis to figure out the sizing. You may need a constellation of satellites rather than just one satellite to accomplish the mission. And for elevators, how many elevators do you need in a building? And so it's going to depend on the number of floors, the number of traffic that is predicted, and various factors. So just some more details on the traffic analysis and sizing. And another discussion here, this is making sure that we use the analytic data properly. And so this is trying to talk about the flaws of averages. Averages, if you use them incorrectly, can cover up things that could really damage what you think would be an acceptable design. For now, we talked about the elevator. We also have talked not as much, but the soda machine analytics. And so here we're mentioning quantitative characterizations of the soda machine. The fundamental objectives of the soda machine performance requirements include threshold and objectives for. And so some of the main things for a soda machine: the mean time between supplies, probability of getting the correct change, or probability of getting the correct soda. Those would be some key performance parameters. And so we're seeing some things similar to the elevator. So threshold and objective values for threshold for performance requirements. We want to examine the stochastic properties of the soda machine. So we have this kind of development for this application. We have the internal inputs, external outputs, and engineered values for the operational phase of the soda machine, as we showed in the elevator example. We have the engineering design problem, and we have the operational choices. There's a couple possible ways that you could implement this, just like we had two choices that we provided for an elevator. Some more details on the operational choices. And now we have the third one, the quantitative characterization of an aircraft. And we talked about an F-22, as well as the payloads that it might have. And so here we're now going through that same process for a third example. We can be thinking about the aircraft engineering design problem. What is it that you're trying to solve with this particular type of an aircraft? You can think of range and endurance would be key things that an aircraft would have, as how long and what velocity would you be able to go at that. If it's going to have a high velocity, chances are it's not going to have as much endurance. And so there's going to be a trade, and you're seeing some of those things here. For a cargo aircraft, now we're trying to see what it would be for a C5A cargo aircraft, say looking at the weight for an empty aircraft, because the lighter it is, it's the more you're going to be able to have for storage for a payload or for things that you're trying to transport from point A to point B. So I'm not going to go into this in detail. There's a lot more points that are trying to be made in this slide as well as in the text. Here's just some more details following on. Now, in terms of another topic, system dynamics. System dynamics it deals with stock flow feedback structure modeling of general various things, such as a General Electric appliance manufacturing plant. And in that scenario, it revealed that the observed 3-year employment cycle of hiring and layoffs was attributable to internal structure of firm and not to external forces of business cycle. So what kind of, just by analyzing the system, you're going to start to find metrics that might be illustrating that you have unintentional consequences that you may need to adjust. Going back to the soda machine, the system dynamics, you can actually come up with a model. And so diagrams like this can actually be helpful for you to be figuring out and optimize what you're trying to do. For constraint theory, this is trying to determine the well-positedness of sets often disparate interrelated multidimensional models. And so do they all make sense? You have maybe some competing constraints, and you're trying to keep those into account as you're completing your design process. For the variable relationships of models are visualized with graphs that provide topological structures of the models. Graphs are mapped to constraint matrices, which then can be computationally solved. And so those are some steps that would take place in constraint theory. So here are some examples of rules to determine consistency of mathematical models. I'm not going to read this, but here is a table from the textbook that gives some examples of things that you can be thinking about. For well-positiveness of elevator system, this is still in constraint theory. And so we can see how well we've laid out the objective hierarchy. And we showed the hierarchy in a couple different forms throughout this course. This is just some more details of that. I won't go through it. And a third chart completing that look at the objective hierarchy, the discussion for the elevator system. So here is a directed graph of the elevator system objective hierarchy. And so now we're getting back to graph theory, and we're showing how this is a very practical for what we're trying to accomplish. Notice that we have a couple different types of elements. There's circles and there's squares, and we talked some examples of the type of diagrams. And so this is a bipartite, directed bipartite graph. We have some more complications that we're trying to capture. Here's an example of a constraint matrix for system objectives hierarchy. And so that's also something that may be of use. Okay, well, we're getting close to finishing this lecture. And I did go through some of that fairly quickly because I wanted to keep it at a high level and sort of give you an overall survey. Since I did the summary at the beginning, I'm not going to do it at the end, but I'm going to focus on a few charts here to talk about some important topics. And first is this idea of guesstimation. And so guesstimation is an approach to make good approximate estimates with little or no data. And so that is an extremely important system engineering skill. And it's important enough that I'm going to be talking about it as part of what I'll be addressing in the next handful of charts. So an unknown and perhaps unknowable dependent variable is determined to within an order of magnitude of its true value. And so you want to be coming up with some method for evaluation and estimation. So you can be doing it by similarity, or just having, if you think of system engineering and just you have a lot of black boxes you're hooking together and you're trying to create some kind of way of having an estimate, this is what you're trying to do here. So the unknown quantity independent variable is estimated by using the, say, a geometric means rather than an arithmetic means. And so this would be an example of a basis of estimates that you're trying to leverage. If the individual estimates of the independent variables are unbiased, then the estimate of the independent variable tends to be within an order of magnitude of the true value as the number of independent variables increase. So I won't go through this, but a famous Fermi problem was to estimate the number of piano tuners in the city of Chicago. And so how could you actually go about doing that? And so you can be thinking in terms of the populations, the percent of the populations that has a piano, the annual rate that the piano is tuned, and the times to tune a piano, and the average time that a piano worker actually works in their employment in a year. And so you can start to put these things together, and that would be one way of coming up with a basis of estimate. So that's the general strategy of what we're trying to talk about. So this is the last slide. So we talked about guesstimation, and this is just reflecting on that from a slightly different point of view. The value of making good approximate estimates with a little to no dating, with little time, is a critical engineering skill in all phases of the life cycle of a system. In the early phases of identification of need, concept definition and preliminary design, determining the technical cost and schedule feasibility is especially critical to succeed. In the latter phases of detailed design, integration and test, production operation, maintenance and disposal, fast approximate estimates provide a sanity check of the more detailed models and data. Okay, well, thank you very much. That's going to end our lecture for this chapter.